Hello and welcome to this lecture. In this lecture, we will learn some of the statistical methods to test the observed data, whether they are fitting to some particular distribution or not. You know that in earlier lectures as well as in earlier modules also, we have referred several times that while handling some problem, we generally assume that the data set that is following a particular distribution, and we have seen now we will see that how we can test these things, that whether the data set is really following which distribution or not. There are some of the statistical tests that I am just going to tell in this lecture is that so to use that one and use the knowledge of this hypothesis testing, we will be testing it statistically, that how the data is fitting to a particular model. So there are some tests, and we will just pick up some of this popular tests to do to see that how we can test this goodness of this test are known as this goodness of fit test. So this is that's the our today's lecture title is the goodness of fit test. So first we will just see that how this can work, and after that we will take two tests for this lecture. That one is that chi-square test. This will be chi-square, not D. D is mistake. That is a chi-square test. Another one is the Kolmogorov-Smirnov test. It is also known as this KS test as an abbreviated form. And this case test again can be that one sample test and two sample test. Basically, when we take that this one sample test, then we generally test it for the for one sample that we take, and we generally take that from whether that particular data set follow a particular distribution or not. So in this case, one is our sample and other one is the standard distribution. And when we go for the two sample test, it is basically both are our sample data is there, and we look for the answer whether both the samples are from the same population or not. So I mean, same population means they are following the same distribution or not. So this is how we go for one sample test and this two sample test. As you know that for this kind of statistical test, we need some kind of significance level, and so some statistical significance level. So whenever we generally conclude or we draw some decision from whatever the statistical test we do, we generally that decision is associated with the statistical significance level. So that is important. So what significance level that we are considering, either beforehand or either beforehand, that okay, at this significance level, the whatever we are going to test is satisfied or not in a statistical sense. That's what we will do. Well, so so now first we will go to this whatever I just mentioned so far, is that it may be necessary to check how well a set of observed data fit to a particular probability distribution, and this can be described using the certain statistical test known as the goodness of fit test. And as also I just tried to indicate that the basic philosophy is to measure the discrepancy between the observed and theoretical values used in the statistical model. So this basically are the general thing for all the tests that we are going to describe now. That and this one what we are describing is particularly for the one sample test. Suppose when we are saying that I have a data set and that follows a particular distribution, so what is our interest is that whether there is any discrepancy between that whatever the observed distribution that we can see from this data and whatever the distribution that we are assuming to follow, whether it is normal or log normal or even in the discrete side Poisson or so. So whether those distribution, that theoretical values and this whatever the observed from this data are matching or not. So that discrepancy we have to see, and that discrepancy we have to decide the which through some distribution we have to draw some inference in a statistical way. So the example of this goodness of fit test may be as follows. Say that what type of question that we are looking for their answer. Say that whether a sample of a discrete variable follows a Poisson distribution or not. So these are just the example. It is not that always I am looking for this Poisson distribution or so. So any distribution. So I know that this random variable is a discrete variable. So I have some I am hypothesize that whether that sample can follow a particular discrete distribution that we know already, and those distributions we have discussed in our earlier lectures, in earlier modules. So like that question, so I have a sample whether that sample follow a Poisson distribution or not. Similarly, whether a sample of a continuous variable follows a normal distribution or not, or gamma distribution or not, or log normal distribution or not, like that. Or in case of the two samples, whether both the samples are drawn from the identical distribution or not. So when we are testing it, we'll just try to take that all these several types of these problems, where we'll try to cover almost all these different cases, the discrete variable case, continuous variable case, as well as the two samples case taken from two different sample we'll take, and whether we'll test that whether they are from the identical distribution or not. So as we mentioned, there are some of these commonly used tests are there. These are the standard tests that we generally use for this goodness of fit test. The first one is this chi-square test, and then the Kolmogorov-Smirnov test, and there is also another test which is the Anderson-Darling test, which is generally known to be a little improvement over this KS test, and we'll take this one also, but maybe for this lecture we'll just consider this chi-square test and KS test. So now this chi-square test, the chi-square distribution is used for testing a goodness of fit of a set of data to a specific probability distribution. For this we make the comparison of the hypothetical frequencies that follow the specific probability distribution. So this is that what we have discussed for this basic philosophy, and this is basically, if you see that that overall approach is same for all these tests. So the comparison of this whatever we have observed from this data and whatever we are supposed to get from that hypothesized distribution, whether they are matching or not. So here basically this chi-square test is based on their frequencies. So we'll find out the observed frequency and also see what is the hypothetical frequencies. And obviously, as we are talking about this frequency, so we have to categorize the data into different bins, and each bin what is the frequency, what is the observed frequency. This observed frequency means whatever the data that we are having, based on that what is the frequency that we can see, and we are hypothesized one distribution. So based on that distribution, obviously the distribution should have some parameters. With that, those parameters, what are the frequencies that we can observe. So, and this one can be used for both the cases, means both for this discrete random variable as well as for the continuous random variable we can use this test. So what is done, that maybe we'll discuss now in a step, in different steps. First of all, let us consider that a sample contains the n observed values of the random variable. So whatever the data that we are having, that is that n numbers of data that we are having. And now this notation, that is O1, O2, O3 up to OK, be the k observed frequencies of the variates and the corresponding frequencies from the assumed theoretical distribution be E1, E2, E3 up to Ek. So this is that observed, that is, this is from whatever the data that we are having is the O1, O2, O3, OK, and this E1, E2, E3, Ek, these are from that whatever the distribution that we are hypothesized that this data set may follow that particular distribution. So from that distribution, whatever the frequency that we are getting is Ei's, and whatever from the data, that is Oi's. So this it is required to test whether the difference between the observed and the expected frequencies are significant or not. So these are the O1, O2, O3, okay, and these are the from the hypothesized distribution. Now their difference, whether if this difference from the observed and to the theoretical is significant, then we can say that whatever the data that we are having is not following whatever the distribution that we have hypothesized. And on the other hand, if they are almost same, then we can say that yes, that is it is following that particular distribution. Now so how to do that one, how to find out that discrepancy is through this parameter. We generally call it as a statistics, and that statistics is obtained as that OI minus EI whole square divided by EI and sum of for all k's, means all these groups, that is from 1 to k. Now this quantity is, as I told, that this is the statistics, and denoted by here is x square, that we have denoted this one, and it has been found that this x square or this statistics, it follows a chi-square distribution if the n tends to infinity, that is that obviously that mathematical limit. For the large number of this sample data that is available, these statistics follow a chi-square distribution, and this chi-square distribution is having some degrees of freedom. Here the degrees of freedom is k minus 1. So this one, so as we know that this particular statistics follows the chi-square distribution with k minus 1 degrees of freedom, that means we know that what are its properties, and based on that, at what significance level I want to test whether this is means significantly this is significant or not, that we have to test. One thing is I should mention here that sometimes it is required, for example, that when we are calculating this EI, it may require to estimate some of the parameter of that hypothesized distribution from the data itself, if that parameter is not known, and in that case as many parameters as you are required to estimate from this data, and then those many degrees of freedom will be lost. So this is if you are not estimating any parameter from the data available, that time the degrees of freedom is k minus 1, but if you estimate one parameter, then this degrees of freedom will be k minus 2. If you are estimating two parameters, then degrees of freedom will be k minus 2, k minus 3. So similarly, so as many parameters you are estimating from the data, those many more degrees of freedom will be lost. So now this one, okay, some more things, some more properties. These are not that means directly I cannot say that why these are required, but for the better results, that is within code, that for the better result, this we should take care before we go ahead with the test. The first thing is that k should be greater than equal to 5, so that number of groups that we have divided that observed data, it should be greater than equal to 5, and that EI is, that is that frequencies that we got in each bin should be at least 5. So this EI should be greater than equal to 5. Now the special case, the most of the cases we may not have the parameters of the theoretical distribution, and then the parameters should be estimated from the data itself, and the statistics remain valid if the degree of freedom is reduced by 1 for every unknown parameter. So that's what I just explained. So if you need to estimate the parameter of the hypothesized distribution from the data, then you need to allow that much degrees of freedom will be lost. Now assuming that the distribution follows as this one that I told, okay, there will be a square here, as you have seen earlier, this statistics, this observed minus this hypothesized square divided by EI and their summation. So if this one is less than this value, what is shown as a C1 minus alpha nu, and this nu, as it is already explained, that this is the degrees of freedom. This C1 minus alpha nu, that is C1 minus alpha, is a value of approximate that is chi-square distribution with new degrees of freedom at the cumulative probability 1 minus alpha. So, now this alpha is that significance level that we are talking about. The assumed theoretical distribution is an acceptable model at the significance level of this alpha. So, this is what that I was mentioned initially, that all these tests should be associated with some significance level. Generally, this significance level are kept around say 0.1 or 0.01 or 0.05 or so. So this at this cumulative probability 1 minus this alpha. So if it is that 5% significance level, if we say, that means that cumulative probability at which we are testing it is at the 95%. So if the observed statistics is less than that cumulative probability of that distribution, here it is a chi-square distribution of this 95%, if the alpha is 0.05 significance level, then we can say that yes, this null that whatever we have hypothesized may not be rejected. So yes, as I told that this would be on the square, as you have seen it here also, these statistics, so y minus ei power square. Now we will take up one example, and this example we have taken for the discrete case, and because this chi-square distribution can be used for the discrete parameters. So we have it can be used for the continuous as well as discrete, but the next one what we are going to cover is the case test, that is for the continuous distribution. So here we are taking a discrete example. Consider a given station in a watershed where the severe rainstorm are recorded over a period of 70 years. Last 70 years we have recorded how many rainstorms are there in a particular year, and out of these 70 years, 22 years were without severe rainstorms. So there are in 22 years there are no severe rainstorms, so number of rainstorms is 0. And 25 years, 14 years, 6 years and 3 years are with 1 rainstorm, 2 rainstorm, 3 rainstorm and 4 rainstorms respectively. So 25 years we have observed there is 1 rainstorm, 14 years we have seen there are 2 rainstorms, 16, 3 rainstorm, and the 3 years there are 4 rainstorms are there. Test whether the data can be assumed to follow Poisson distribution at 5% significance level. So here, as you can see that we have hypothesizing that whether the data that is given, that whatever we have recorded, whether it is following the Poisson distribution or not, and the significance level is given as the 5%. So here now you see, so the Poisson distribution, you know, there is some lambda, there is one parameter that we have discussed earlier modules, that parameter, that lambda is the mean rate of occurrence. So the average occurrence rate. So average occurrence rate of this rainstorm, if we want to calculate, then we have seen that there are 22 years where there is no rainstorm. So 22 multiplied by 0, basically the first thing. Then 25 years 1 rainstorm, 14 years 2 rainstorms, 6 years 3 rainstorms and 3 years 4 rainstorms are there. There are total. So in this way, out of the 70 years, what are how many total rainstorms that you have seen, that divided by 70 gives you that average rainstorm that can occur in a year. So 1.1857 rainstorms you can see in a year. So lambda here is that 1.1857, and the t that we are, the lambda t, that is the total quantity, the t is here the per year. So 1 year how much rainstorm has occurred. So this is the quantity, the 1.1857. Now remember that we have estimated this one from the data itself. So this was not supplied. Sometimes what happens, this data would have been supplied directly, whether the data is following the Poisson distribution with the lambda is equals to say 1.3 or 1.1 like that. If that is given to us, that means we are not estimating that one from the data. So there's degrees of freedom, whatever we told, that it is k minus 1 will be there, but here we have already estimated one parameter. So now the degrees of freedom will be k minus 2. So So, now to check the goodness of fit, we use the chi-square distribution at alpha equals to 5% significance level. As the data is so small, the data for the 4 storms per year is combined with the 3 storms per year. So, this one is generally done, but so there is some discussion is required. We can so now we have to think that what distribution you have hypothesized. So, it is the Poisson distribution that you have hypothesized, and what is the support for that distribution. Now, the Poisson distribution, that support that we are looking for is basically starting from the 0 to 0, 1, 2, the discrete values, and goes up to infinity. Now, the data that is obviously is given to us is that 1 rainstorm, 2 rainstorm, 3 rainstorm, and up to that 4 rainstorm per year. But when we are hypothesizing that this is the Poisson distribution, obviously I cannot curtail at any particular point. So, here what is the general practice is that for the higher side where the data is becoming very small, we can combine those things to take care of two things. One is that, so I can declare that yes, more than equal to this value is having this frequency. And the second thing is that we will also be you will also be testing whether that each group is having that minimum requirement of this frequency is available or not, because this kind of asymptotic distribution, that is, it is going towards the plus infinity. So, there this type of, it should be open bounded, but the way the problem is given, it is just as a closed boundary at 4 rainstorm per year. So, here if we just consider that the 2 rainstorms are combined together, that is a 3 rainstorm per year and 4 rainstorm per year case, then we can say that greater than equal to 3 rainstorm per year. So, that remains that positive side remains unbounded, and also this will help to check that whether that frequency at each cell is at least greater than 5, that is for the better result that we have mentioned earlier. So, here also what we are doing is that the 4 storms per year and the 3 rainstorms per year are combined together. So, here the null hypothesis is the random variable has a Poisson distribution with lambda equals to 1.1897. Alternate hypothesis is the random variable does not follow the distribution specified in the null hypothesis, what is specified here. Significance level is 0.05 at 5% significance level mentioned, and we have the k equals to 4. So, the degrees of freedom here is a k minus 2. So, k minus 1 is from there, and one parameter we have estimated. So, it is k minus 2, the degrees of freedom is 2. So, the critical region here is this chi-square distribution, that is chi-square distribution with 2 degrees of freedom at alpha equals to 0.05. So, now if we see, so this is that chi-square distribution table. Basically, you know that we have discussed this distribution earlier, and the standard values are listed in any standard textbook. So, here if you see that this point at this 0.95, this is the cumulative probabilities are given here, and for this degrees of freedom 2, this value is 5.99. So, this value is our that critical value that we have to test against. So, this is that 5.99 that we got from this table, and these are the bins here now. So, 0 rainfall, 0 rainstorm per year, 1 rainstorm per year, 2 rainstorm per year, and this is that greater than equal to 3 rainstorm per year. So, now this, as it is given in this data, that there are 22 years where these 0 rainstorms are there, and the 25 years where there is that 1 rainstorm, 14 years 2 rainstorm, and 6 years 3 rainstorm, and that 3 years 4 rainstorms are there. So, we have combined it here to get the 9 years data where it is greater than equal to 4 rainstorm per year. So, so we have avoided that in one occurrence it is becoming 3, which is less than 5. So, that is also avoided, and that right side is kept open. And the theoretical frequencies, that is these values, what we are getting is that, you know, that this from this Poisson distribution, that lambda t here equals to this lambda equals to that 1.18 1897 and t equals to 1, so 1 year. So this lambda t value we get, and from the Poisson distribution if you just put that x equals to 0, x equals to 1, x equals to 2 and x equals to 3 with that value of lambda t equals to that value, then we will get these values, which are the, so these are the theoretical frequencies for this Poisson distribution. So now this is, so these are, so this value you are getting when you are putting this x equals to 0, and this value you are putting when you are putting x equals to 1 from this Poisson distribution. So this is the theoretical frequencies and these are the observed frequencies. Now what we have to do, we have to get this statistics, that is y minus ei whole square divided by ei. So if we do this one, then we will get these values and we have to sum it up this one. So this is the summation from, is that 0.1668. So this one, this is our the stress statistics, which is equals to 1.668 that we have seen from the table. So so which is now is the less than 5.99 that we have seen from the table. So this is less than this critical value. So hence the Poisson distribution is a valid model at 5% significance level. So the decision is that for this test is that the null hypothesis cannot be rejected at 5% significance level. So there could be some other words that we can express, okay, the null hypothesis is not rejected and all. So what I feel is that this would be the proper decision, proper probabilistic or the proper statistical inference should be written as this one, that null hypothesis is accepted is not the right thing to declare. So rather the complete thing that we can declare is that the null hypothesis cannot be rejected at 5% significance level, because the result that you have got, it depends on the what significance level that you have opted for. So that is what we have to mention, that at this significance level the null hypothesis cannot be rejected. Okay. So next we will go to that our second test, which is the Kolmogorov-Smirnov test. In brief, we generally mention it as a KS test. This test is also most commonly used to check the validity of the assumed model, and it is not applicable for the discrete variables. So mostly that continuous random variables, if the data set is available, for with that we generally get this one. It relates to the CDF rather than the PDF to a continuous variable. So here earlier what we have seen, that the frequency that when we are talking about in this chi-square test, that is basically a PDF that we are talking about. Here this case test is generally based on this, what is their CDF, that is cumulative distribution function, and it compares the observed or database cumulative frequency with the assumed theoretical cumulative distribution. So database cumulative distribution, sorry, this should be distribution with the assumed theoretical cumulative distribution. So there are some kind of discrepancies or the shortcomings, I should say, in this chi-square test, is that we need to define that we need to first of all get that bins, that we have to first categorize the data set, the full data set, that is okay, this is my range, and in the discrete it is okay, fine, that whatever the example that we have seen. Now in for the, as I told, that this chi-square distribution is also applicable for the continuous distribution. Now if we take some continuous distribution in case of the chi-square test, what we have to do, we have to first categorize the data into different bins, and each bin we have to see the frequency, and also we have to check that whether each bin is having, so the number of bins should not be less than 5, as well as each bin should have minimum, that minimum frequency should be 5 for the better results that we have mentioned. So these two things are not there in this case test. So it is directly getting assess its results from the CDF itself directly. So there is no need to categorize the data into bins, and so it is avoiding those requirements of this minimum 5 bins, and that each bin should have the minimum frequency of 5, so which is not there in this case test. Now, so if suppose that there is a random variable x and we have some data set of this x1, x2, x3 up to xn, so represents the ordered sample of size n. So, whatever the data that we are having from this actual observation, we can first of all we can make it in an arranged in an increasing order, and that increasing order, if that increasing order is that x1, x2, xn, if that is available. Now, from this ordered set, the empirical or sample distribution function Snx is developed, and this function is basically a step function. So, this is from this data. So, how from this sample how to get that get that this cumulative distribution function is as follows. That is, for when this Snx is equals to 0 in case when x is less than x1, Snx is equals to k by n when this x is in between k to k plus 1, and k can vary from 1, 2, 3 up to n minus 1. So, basically for all this x1 to xn, for this thing we are defining this value, the value of this cumulative distribution is k by n, and for x greater than n it is equals to 1. So, this is basically what we are getting is the whatever the representative cumulative distribution from directly from the data, and each point it is changing, this value is changing. So, it will look like a step function. So, obviously as you can see, this Sn will start from a value 0, it will start from a value from 0, and so at some point it will increase, and again from the next one it should go, and like this it will go somewhere, it will go flat, and in this way what will happen, it will ultimately attain the value where it is 1. Now, this is the distribution basically we got it from this data. Now, the hypothesized distribution, suppose that I want to match that that normal distribution. So, that normal distribution with the parameters, of course, whether it is supplied or obtained from this sample data, is that with that data I can also plot what should be the shape of this that particular distribution, say that normal distribution if I say. Now, if this whatever we have observed, the black line here, if this is very close to this red one which is the theoretical distribution, obviously then the data is from that particular distribution. So, this discrepancy, now again that's keeping the same approach same for the all the tests that I mentioned at the beginning of this class, is that here also we have to see that what is the maximum difference between these two distributions, that CDF. So, one is the theoretical and other one is the database. So, that discrepancy we have to assess through some statistical test. This is what that is why we have got this Snx. So, this Snx is a step function, and this Fx is the proposed theoretical distribution, that what I have drawn in the red ink just now. So, now here if you see, the discrepancies between the theoretical model and the observed data is computed, and the maximum difference, the dn between the Snx and the Fx is over the entire range of x is obtained, which is denoted as dn, which is the maximum for all x, Fx minus Snx, obviously the absolute value. So, now you can see here for a particular point here that you can see. So, this is from the blue one that I have drawn, this is also a step function here, the blue line, and this pink one is that your is the theoretical distribution. Now, the difference between any point to that that theoretical distribution is your, that value is the difference between two things. Now, what we have to pick up from this two information is that what is the maximum difference. So, at each point there will be some difference between this blue line and this pink line. So, that difference at each and every point I have to find out, and we have to select, we have to pick up the maximum one. So, what is the maximum difference? This blue line, obviously as we are coming left towards this is 0, and from where it is ending towards the right to that one, it is equals to 1. And so, over this entire range we have to pick up what is the maximum difference. So, thus for a specified significance level at alpha, that case test compares the maximum difference with the critical value dn alpha. Now, what is this dn alpha? This dn alpha is defined as the probability that dn less than equals to dn alpha is equals to 1 minus alpha. Again, this alpha here is that significance level that we have mentioned at the beginning of this class. So, if the observed value is less than the critical value, then the proposed distribution is valid at the significance level alpha. So, we have to check that whether whatever the maximum difference that we get and whatever that critical value. So, this probability, that is that observed dn less than equals to that critical value, whether it is equals to this 1 minus alpha or not. Now, the advantage of this Ks test, as in the chi-square test, the division of the data into interval is not necessary in this case. So, I think these things I was just mentioning while at the starting of this Ks test. So, these intervals are not necessary here, because we are just observing this thing at each and every data point. The test statistics is distribution free, unlike in the case of the distribution of the chi-square test. It works for this non-normal data. However, the test can fail if the data is too far from this normality. So, so there is no such restriction that with the data should be approximate normal or so, but it is better to get the better result again, that data should be somewhere somewhere near normality. That is why the popularity of this Ks test is, we have seen it is very frequently it is applied to test whether the data follow the normal distribution or not. That is where the maximum application of this Ks test has been found. Now, the sample distribution, if the sample distribution that n is large, not the distribution, sample size, if the sample size n is large, the Smirnov has given the limiting distribution of square root n multiplied by this dn. So, this is the dn that we have defined, the maximum difference, that multiplied by square root n, this quantity follow a distribution like this, that limit n tends to infinity, probability of this quantity square root n multiplied by that dn, the statistics, less than equals to z is equals to square root 2 pi by z multiplied by summation of k equals to 1 to infinity exponential minus 2k minus 1 square multiplied by pi square by 8z square. So, this is what it is giving, is that for this n tends to infinity, means when this n is very large, that time what we can get is that how this dn is varying is that through this, that we have to find out, suppose that suppose now, so it depends on this what is the significance level that you have fit. Suppose that this significance level, if it is 0.05, that means this probability is equals to 1 minus alpha, that means it is 0.95. Now, if we solve this right hand part with equal to that what is that 0.95, then we will get that is z becomes 1.36. If you see this quantity here inside this exponential term, that is 2k minus 1 whole square multiplied by pi square by 8z square. So, this term basically is changing, that is from this k equals to 1 to infinity. Now, if k is 1, you can see that this is just minus of this quantity plus exponential of, if k becomes 2, then it is becomes 9, so minus 9. So, exponential minus 9 times of this one, and if k becomes 3, then it is 25 times of this one. So, basically if you just do just a hand calculation also, you will see that if you just consider the first term itself, that is k equals to 1 only, and remaining if you just ignore it, then also you will see for this this is almost very closely matching with this one, maybe it is just varying after third decimal or so. So, for this n greater than 50, sometimes in some textbook it may refer to that if is n is greater than 35 itself, and for this alpha equals to 0.05, that means this right hand side is equated with this 0.95, and if you just calculate what should be the value of this z, if you just consider only one value of k equals to 1, then you will see that this z becomes very close to this 1.36. So, for this significance level alpha equals to 0.05 0.5, that critical value is 1.36 divided by square root of n. So, that means this z becomes 1.36 and this is that 1 square root of n. So, so this critical value, this should be, so our observed statistic, that is dn, should be less than this particular value to declare that at that significance level the we can accept that particular hypothesis, or that null hypothesis cannot be rejected. And similarly, if we put that say alpha equals to 0.1, that means this right hand side if we equate to with that 0.9, then we will see that this quantity, this z is becoming 1.22. So, the critical value is 1.22 divided by square root n. And for these lower values of n, this is also available in the standard table from that distribution, and we can refer to those tables to get that this critical values. So, we will take up one example to just to discuss all these things, and here we have taken one example of this continuous random variable. And as I mentioned that this is mostly used when we are considering that when whether the data set is following normal distribution or not. So, the data of the fracture toughness of the plain concrete specimen made with the burnt brick aggregate is shown in the table in the next slide. The data appears to fall approximately a straight line on a normal probability paper, that you know that if it falls approximate normal on the normal probability paper, there is a possibility that it may follow a normal distribution. And that the parameters are that mu equals to 0.54 and the sigma is equals to 0.051. So, perform the Kolmogorov-Smirnov test at 5% significance level to statistically justify the assumption of the assumption for the given data. So, data is supplied here, that is the fracture toughness, which is having an unit of megapascal square root of meter of the plain concrete specimen, and this is already arranged in an increasing order. So, you can see that. So, that there are total 25 samples are there, 1 to up to this 25, and this one, that KIC, which is the notation for this fracture toughness, is arranged in an increasing order. So, from 0.451 to 0.658. So, we have to test that whether this data set is following the normal distribution or not, and normal distribution having the parameters 0.54 and 0.051. So, our null hypothesis here is the random variable has a normal distribution with those parameters. Of course, alternative hypothesis, the random variable does not have the specified distribution in this null hypothesis. Level of significance is 0.05, and the critical region from the table I will just show, that is here what are the number of data is the 25 that is available, and significance level is 0.05. Now, if you see this table here, that is these are the values of this case test, goodness of fit test. This is that for different n, the n is listed in the first column 10, 11, 12 like this, and this the second one is that is your alpha 0.05. So, this kind of table is available to any standard textbook, and here if you just see this value is highlighted for this n equals to 25 and the alpha equals to 0.05, the value is 0.264. So, from this table we have just picked up this the critical value of that test. Okay. Now, if we just do this one, do this same method that we have explained now, whatever the data that we are having, we have just we have plotted it for its distribution with this step function shown in the blue line here, and the theoretical distribution for this normal distribution, that CDF of this normal distribution with parameter 0.54 and 0.051 is shown in the line magenta. Now, whatever the maximum difference between these two, that we have to pick up. So, the cumulative frequency of the given data is plotted in this figure with respect to the equation of this case test, and the theoretical distribution function of the normal model is also shown, what is shown here. From the figure, and of course, you can check it in this calculation also, the maximum discrepancy of the two functions are d max equals to 0.1348, which is occurring at KIC equals to 0.508. So, at this value the d max is 0.1348. So, this is the only value that we have to pick up from this comparison. This is what that that case test, and sometimes from this point onwards maybe that further improvement we will look for, that is, but that is the later part. But here from this graph only one information that we are picking up is the what is the maximum difference. That's one particular value we have to pick up, and that value is 0.1348. The maximum discrepancy 0.1348 is, now we can test that it is less than that critical value that we have seen, that is, which is the critical value is 0.264 that we have seen from the table. So what we can see here, so this model that is with this, that is a normal distribution with parameter 0.54 and 0.051 is a valid model at 5% significance level. In other words, or I should say that this should be used to declare that the null hypothesis cannot be rejected at 5% significance level. Well, now we will go to that two sample test. Keeping the basic philosophy again here is the same thing. One is that, so in the one sample test, what we have done is that one, the data that you have obtained, and other one is that some standard distribution that you already know. So in the example we have seen that one normal distribution that you have used. Now the two sample test means that we are not using any standard distribution. The two samples are there. Two samples both will have their own data-driven, that observed cumulative distribution function, and we have to pick up the difference between two. So so in the one sample test, basically that is one observed data, other one is the some standard known theoretical distribution, and in two sample test both are the observed data, and we are plotting, and what the value we are picking up are exactly the same thing. So the same test used in the case of the one sample test can be used to evaluate whether the two samples come from the same distribution or not. Let the maximum absolute difference between two empirical distribution function be dmn. Now let the two functions be represented as the step function gmx and snx based on the two samples of size m and n respectively. So that two samples are there, one sample is having the m data, other one is having n data. So this should be flexible. It is not that both the samples may not have the same size of this data. And what we have to what we have to get is that from here is that we have to find out what is the gmx and what is the snx, and following the same equation that we have shown in this one sample test using case test. So thus here the difference will be that maximum difference that we have to get, which is the absolute value of this difference between gmx and that snx, and that one we have just pick up only single value, again similar to the one sample test, which is denoted as that dmn. This m is the size of this one sample, other one is the size of the other one. Now this is one such typical example how it will look like. The blue one is for the one sample and the red one is for the another one. So now we have to find out. So basically the red is again approaching towards this, all are 0 value here, and here also red is going, all are 1, values are 1. So now each and every point we can find out what is the difference there. So at this point maybe around minus 0.4 or so, the difference is shown here between this point and this one. This is the dmn for this particular value. So for all such differences we have to pick up the maximum one. So this case test for the two sample goodness of fit as looks like this, and we have to pick up the maximum one. Now again the sample distribution have the large values of the m and n. If these values are large enough, that's m and n. The Smirnov has given the limiting distribution as this. The square root of mn by m plus n, which is the data size for the two samples, multiplied by this dmn less than equals to z is equals to square root 2 pi by z summation of k equals to 1 to infinity exponential of minus 2k minus 1 square multiplied by pi square by 8z square. So basically what happens from the single sample, it was here, it was square root n, and for the 2 samples test it is replaced by the square root of mn by m plus n. So basically the sample size in the 1 sample test we have used that it for this n, and for the representative sample size for the 2 sample test is this quantity mn by m plus n. So if we just change this one, so if we once we are having this 2 samples, so the what is the representative data length, if we have to calculate first, and the remaining thing is same whatever we have discussed for the 1 sample test. That is, if we take that the significance level is 0.05 say, then this quantity if we equate with this 0.95, then it will again come that same value, which is 1.36. So now the critical value, that is the dmn, should be less than equals to 1.36 divided by the square root of this full quantity. Earlier it was square root of n, now it is square root of this mn by m plus n. That is the difference. So we will take one example here. The table showing the modulus of rupture data for 2 different groups of timber is shown in the next slide. Supplier delivered items in 2 lots. The first lot consists of the 50 samples and second lot consists of 30 samples. Both the lots were supplied by the same supplier, and the second lot is claimed to be superior to the first lot. Apply the case test, the Kolmogorov-Smirnov test, 2 sample test, to verify whether the 2 samples are of the same type or not. That is, whether in the statistical sense we should say that whether both the samples are from the same population or not. So this is what we have to decide, and this 50 samples and 30 samples for all these timbers, what is the modulus of rupture is shown in this table. This is the first lot, that is lot A. This modulus of rupture is given in Newton per millimeter square. So this is 35.3, and like this you can see that this is a 5 by 10 column. So all this data is refers to the modulus of rupture for the 50 samples supplied in lot A. Similarly, in the lot B, these are 30 data points of this modulus of rupture in Newton per millimeter square, which is supplied in the lot B. Now we have to test whether both this data set is the same, is from the same population or not. So the null hypothesis is that the random variables sampled by the first 50 values and the random variables sampled by the next 30 values have the same distribution or not. And so, and the alternative hypothesis is that the random variable have the different distribution. So whatever we have hypothesized in the null hypothesis is not valid. Level of significance here is 0.05, and the calculation that we have to do is that the data from the each sample are ranked separately. So we have to make it, we have to sort it. In the last example it was already sorted and that data was supplied, but here we have to sort it. First we have to give the rank, and from there we have to calculate their respective cumulative distribution. So both are that step functions. The samples are sorted in an increasing order and the rank accordingly for both the samples GMX and this SNX are determined as shown in this table in the next slide, and then the step functions for the both samples are plotted. The maximum absolute difference between the empirical distribution is then determined. So the basic steps what we have seen in the single sample and these 2 samples are same. So this is for the first lot, and you can see this rank 1, 2. This is a sorted. This table is sorted just to accommodate in a single slide. That the rank is 1, 2, 3, 4, and it is continuing up to 22, 23, 24, 25, 26, 27, and going up to 50. Now this is that value of that k by n, that is at rank m by n. So it is 0.02, 0.04, 0.006, like that. From this 0 it will go on and it will come to that 1. So this is for this lot A, and similarly this is for the lot B. And if we plot this one, it looks like these 2 plots are there. One is that shown by red and other one is that blue. And now the maximum difference, we can observe that difference and we can get it, and this maximum difference is found to be 0.12. And as I told that now this there are two samples, the one is that m is the 50 data samples and n is the 30. So, if we just get it becomes at 18.75. So, we have to see what is the critical value against this sample size of 18.75. And here if you see that this is approximately we have taken is a 19, and obviously that for the proper value we can go for this linear interpolation between 18 and 19, and but here we have just taken this 0.031 as against this n equals to 19, and this dn 0.05, which is this significance level for at 5% significance level. So, this so 0.12, that's what the maximum difference that we got here is now less than the critical values of this point, critical value, not s. So, critical value of 0.301, which I have seen from this table. So, thus the null hypothesis cannot be rejected at 5% significance level. So, that means both the samples are basically from the same population. So, what the supplier has claimed that the second sample is superior than the first one is not valid at least at this 5% significance level. So, in this lecture we have discussed two statistical tests to test whether what type of particular distribution a particular sample is following through two statistical tests. One is the chi-square test and second one is the Ks test. Generally the chi-square test can be applied for both that discrete and continuous random variable, and this Ks test is for the continuous random variable, but most of this application whether the data set is following the normal distribution or not, that we test, and also we test that whether the two samples that we are having whether they are following the same distribution or not. That's what we can test using this Ks test. So, we will take up some other test in the next lecture. Thank you.